All right, everyone. Assalamu alaikum. Let's begin. So we were doing trigonometry, and we were actually doing the last concept that we have in this topic, and that's trigonometric graphs, right? That's what we started doing in the last session. In fact, we were done with a major part of that. So we started with the sine graph. It looks like this from 0 to 360, and then it just keeps repeating itself beyond this interval. We talked about cos x. This is what the standard shape of cos graph looks like, and also is a cyclic graph. It repeats itself beyond 0 and 360. And similarly for tan, we had this graph. This is also a cyclic graph, but it's broken like this, right? So you have some asymptotes in this graph at 90 degrees and at 270 degrees. In radians, you can say at pi over 2 radians and at 3 pi over 2 radians. The graph is broken at those points. And we learned how we can draw this shape like this. We also learned about the table function, right? How we can use the table function. That's going to be very helpful. Otherwise, it will take a lot of time to draw it like this, to have all of these values. You do not even need to show all of these values in your working. You can just use the table function and just plot the values directly from the calculator. So you don't have to show these values here on your working. That's what we learned. Then we talked about different terminologies that you have to use, that you need to know about. Period. Period is the interval in which the graph completes one full cycle. So we talked about how the periods of sine and cos graphs are 360 degrees or 2 pi radians. For tan, however, it's 180 degrees or pi radians. We talked about the baseline. Baseline is the line about which the graph moves up or down. It's exactly in the middle of the maximum point and the minimum point. It's a horizontal line. And amplitude is the maximum displacement of the graph from its baseline. So from the baseline, what's the maximum displacement vertically upwards and downwards? That's what the amplitude represents. Okay, so after talking about those graphs, we started talking about vertical transformations of these graphs, right? We did not do horizontal transformations yet. We will be doing that today, and then have a look at some practice questions after that as well. So we looked at vertical transformations first of all. This is how the vertical transformations look like. You can either have something, so whenever you have vertical transformations, remember, some operation will be applied outside the function. So this is sine x. Anything that happens is going to be outside the function. Outside the function, you'll either be multiplying with something or multiplying with a negative sign, multiplying by a number, or you might be adding or subtracting something outside the function. So in vertical transformations, now this is going to be handy later on as well when we do functions. So let me just write it down. In vertical transformations, remember, only the y coordinates change, right? That's why we call them vertical transformations, because there's only movement in the vertical direction. Only y coordinates of the graph change in vertical transformations. And looking at the function, if the function is, for instance, sine x remains as it is. Something happens outside the function. So multiplication, division, or subtraction, or addition. So let me just write operations. You can say some operations, which means addition, subtraction, multiplication, division. They are applied outside the function. Right? So in this case, sine x remains as it is. Outside sine of x, we are multiplying by a number or a negative sign or adding or subtracting something. Okay? When you multiply by a negative sign, there is reflection. We call it vertical reflection, but the line of reflection is x-axis, because If the x-axis is the line of reflection, the points that are above the x-axis, they will move below the x-axis. The points that are below the x-axis, they will move above the x-axis. So the movement of the points is vertical. That's why we call it vertical reflection. But the line of reflection is x-axis. If you multiply by a number outside, we call that a vertical stretch. In case of sine and cos, that number is the amplitude. So for instance, if the function is y equals 2 sine x, it means the amplitude of this graph is going to be 2. Okay? And then if you have something added or subtracted outside, that is translation. When you do translation, when you add or subtract something, there is translation, vertical translation. The graph moves up or down. The baseline of the graph, that shifts up or down. Okay, so if you have, for instance, sine x plus 3, we look at this example, the baseline moves to y equals 3. All right, so these are vertical transformations that we talked about yesterday. Let's talk about horizontal transformations now. What happens in horizontal transformations? Something is changed inside the function. Something is changed inside the function. Let's see what happens in this case. Again, let's go back to Desmos. We were using that for the transformations that we learned about yesterday. So let's say we've got y equals, let's do cos function now. Cos of x. What does the cos graph look like? Y equals cos of x. And the graph looks like this. Y equals cos x, right? It starts from 1, then it goes to -1, then it goes back to 1 like this. Now the scale is a bit weird. Let me change it to, first of all, degrees, so you understand that better. And remove the minor grid lines, x-axis, the step should be 90, let's say. Okay, and let's make it -360 to 720, this step to 1. Okay. So that's how the cos graph looks like, right? From 0 to 360, this is the part that is one complete cycle. Now, if we change something inside the function, if we replace x with something else, let's see what happens to the graph in that case. So first of all, what if we do y equals cos of x plus 90. Any idea? What do you think? What do you think is going to happen to this graph? Cos of x plus 90. If we add 90 inside, remember what used to happen in vertical transformation? The graph would move vertically up or down when we added or subtracted something to the function outside. Now what we're doing is we're adding something to x. We have x plus 90 here. What is the graph going to look like in this case? Anyone?
It's
It's
gonna
gonna
look like a
shift
sine
ahead.
graph.
Okay, so there were two people speaking at the same time. Can you repeat Hazim and Rajal one by one? Hazim? Yes?
It's gonna look like a sine graph because all the points will move back by 90.
Okay. Rajal?
Yeah, I was gonna say this.
So you're saying it will become the sine graph?
Yes, sir.
Yes.
Okay. Who else was saying something? Ima? So let me start with this first. So let's not talk about the sine graph or not, for now, let's say this was x plus 45, let's say. Okay. But even this is not going to be sine graph, by the way, not exactly. So I'll show that to you. But let me try 45 first. And let me just change the steps a little as well. And let me make it 45 so that interval is also visible to us. Okay, so what if we have x plus 45? What happens in this case? So how would you describe this? So without involving the sine function, how is the graph going to move? Aima, you were saying something?
No, sir.
Okay. Rajal and Hazan.
Yes, sir. It's gonna shift ahead by 45 degrees.
Shift ahead. Shift ahead. What does ahead mean? Right or
Add
left?
45. Right.
Sure. So you're saying it should move right by
It's gonna
45.
shift left.
Okay. Hazan is saying it's going to shift left by 45. Okay. Anyone else? Any other possibilities? These are the only two options, right? It's horizontal shift, so it's either right or left. Now, which one of the two is it going to be? Let's try to understand this. Now, in horizontal transformations, what happens is, if we had this original function, cos of x, and if we had cos of x plus 45 along with that, let's think about both of these functions together. If we were to input x equal to 0 in the original function, what is the result going to be? The result is going to be cos of 0. Is it not right time? The result is going to be cos of 0. Right? If I input x equal to 0, this results in cos of 0. Now, if I want the same result from the second function, what value of x would I need to input there? From the original function, if I input x equal to 0, that gives me cos of 0. Y turns out to be cos of 0 in that case, right? What if I want the same value of y from the second function? What value of x would I need to input there to get cos of 0? I want to make this thing 0, right? X plus 45, that needs to be equal to 0. If x plus 45 equals 0, the value of x that we input there is supposed to be negative 45. Right? That is what is going to give us the same result. Because if we have minus 45 here, minus 45 plus 45, the result is going to be 0. And that gives us cos of 0. So the result that we were getting earlier from x equal to 0, now we are getting that same result using x equals minus 45. Let's take another example. Let's say we had some other number. Let's say x equal to 90. If we input x equals 90 in the original function, cos x, the result turns out to be cos of 90. If we want the same result from the second function, what value of x do we need to input here? In order to get 90 inside the bracket, x will need to be 45. Okay. So the result that I was getting at 90 before, now I will get that same result when x is 45. That leads us to this conclusion that the point at x equals 0 is now going to move to negative 45. And the point at x equals 90 is going to move to x equals 45. So what was the point at x equals 0? This was the point at x equals 0. This is going to move 45 degrees to the left to minus 45. And the point at 90, which was here, that is going to move 45 to the left here. And that is exactly what's going to happen to every single one of these points. And the graph is going to shift to the left by 45 degrees using this reason, this logic. This is what it looks like. Does that make sense? So in horizontal transformations, it works a bit counterintuitive in the sense that when you do plus inside, the function actually moves towards the left. When you do minus inside, the function moves to the right. And this is the logic for that. Okay? Because the same point now comes 45 degrees earlier. It comes 45 degrees to the left side. Every point moves to the left side. Is that okay? So the conclusion from this is, if we have, for instance, y equals cos of x minus 45, what is this 45 degrees doing? It's basically shifting the graph to the left, right? So minus 45, it shifts the graph, or we should actually use the translation terminology. The graph is translated 45 degrees to the left. And we will learn later in functions that we should actually be writing this as a vector, which is minus 45, 0. That's the translation that's happening. Minus 45, that's the x component. And I'm sorry, did I? Okay, I'm sorry, I wrote minus 45 here by mistake. This was plus 45, right? That's what we wrote there. X plus 45, yeah. It got erased, I think, when I undid something. Okay, anyway. So this was x plus 45, I'm sorry. So translation, 45 degrees to the left, that means the translation vector is going to be minus 45 and 0. All right. So when we do plus in a horizontal transformation, that means the graph moves to the left. When we have a negative inside, then the graph moves to the right. Okay. So in horizontal transformations, it works the other way around. Plus means left, minus means right, if it's in the function like this. Is that okay to everyone? Any problem with this? Any problem with this, anyone?
No, sir.
No? Okay, let's consider another situation. Okay, let's consider another case. Let's say, so let me actually show this graph to you first. So this is what it looks like. The blue graph, that's the translated graph. And if I did x plus 90, like I was saying before, that does not exactly become the sine graph. X minus 90 would become the sine graph. X plus 90 actually becomes like this. Right? So it's the sine graph flipped, basically, reflected in the x-axis. It's not exactly sine. If we do cos x minus 90, that's what gives us that sine graph that you were talking about. Because in this case, the graph moves 90 degrees to the right. Okay, when you have minus in the function, the graph moves right. When you have plus in the function, the graph moves left. Okay, so that's about translation. What if x is multiplied by something or divided by something? What happens in that case? So let's say we have cos of 2 times x. What about this now? So think about it. I'll ask somebody to explain this to me. Somebody other than Hazen. Take 30 seconds and let me know what it should be. I'm just going to connect my charger to this other device. Think about it and then let me know what we should be doing. Yes, what do you think? What happens in this case? Cos of 2x. Cos of 2x, how's the transformation going to look like? Okay, so let's think about this now. So cos of 2x, let's use the same logic as before. So we think of the original graph and the transformed graph. The original graph is cos of x, and the transformed graph is cos of 2x. Now what happens is, if we had x equals 0 in the original graph, what would that give us? That would give us cos of 0. How would we get that same point from the other graph? From x equals 0 as well, right? And cos of 2x as well, if we put x equals 0, that gives us cos of 0. If we had, however, x equals 90 in the first function, the result would be cos of 90. How are we going to get cos of 90 from the second graph? What value of x would we need to input so that it becomes cos of 90?
45.
45, right?
45.
45, right? Yeah, 45. So instead of 90, we have to put 45. So the point at x equals 90 now moves to x equals 45. Okay, let's try another. Let's say we have x equals 180. That gives us cos of 180. What value of x would we have to input in the second function to get that same result? What value of x do we have to
90.
input here? 90 now. So instead of 90, we have to put 45. Instead of 180, we have to put 90. So you see what's happening? Every x coordinate is being divided by 2. So this original point, the one that was at 0, that remains where it was. This does not change. So because 0 over 2 is still 0. However, the point at 90, where is that going to go? That's going to go to 45. The point at 90 goes to 45. The point at 180, where does that go? That goes to 90. The point at 270, that is going to go to 135. 270 divided by 2, that's 235. That goes here. And the point at 360 is going to go to 180 instead. And now that one complete cycle that we had from 0 to 360 degrees, now that cycle is completed in just 180 degrees. So when we have 2 times x here, the period of the graph, which was earlier 360, now it becomes 180 instead. It's divided by 2. Okay? And we will learn later in functions, in function transformations, we can call it a stretch as well, with a scale factor of 1 over 2. So it's a compression in a way. The graph is compressed. It's a stretch with scale factor 0.5 or 1 over 2. Okay? So again, it's the other way around as compared to what we might think intuitively. We are multiplying by 2, but it's a stretch by a scale factor 1 over 2, the reciprocal of that. Okay? So let me show this graph to you. This is what the blue graph, the transformed graph, looks like. Earlier, its period was 360. Now it's 180. Earlier, it was completing one cycle in 360 degrees. Now it's completing 2 cycles in 360 degrees. So you could also think of it in terms of frequency in a way. That, okay, earlier in 360 degrees, it was completing 1 cycle. Now it's completing 2 cycles. So its frequency is kind of doubled. Okay? That's another way to think about this. That's what happens when we multiply something inside the function. That's horizontal stretch. And in this case, we say the period is changed like this. Okay. Now I'll summarize this later. let's just quickly do the last type of transformation as well. And that is, so we've talked about what happens if we add or subtract something inside. So if we add something, we saw that if we add something, the graph moves to the left. If we subtract something, the graph moves that many units to the right. Okay. If we multiply something, the period is divided by that number. So earlier it was 360, now it becomes 360 over 2, which is 180. If we do something like this, for instance, x over 2, or maybe x over 3, can you guess what's going to happen in that case? X over 3. What would the change look like?
It's going to be then multiplied 3 times.
The period, which is 360 right now it will become multiplied by 3. 360 times 3, that's 1080. The graph is going to complete one cycle in 1080 units. Let's see that. This is what the graph looks like. It completes one full cycle from 0 to 1080. So period multiplies by 3 here. So in horizontal transformations, it works counterintuitive. Plus means left, minus means right. Multiplication means that the period is divided. Division means that the period is multiplied. Okay? So it works the other way around in horizontal transformations. Okay, now what about multiplying by a negative sign? So if we have minus times x inside, cos of minus x. Now, when we had negative sign outside, that meant vertical reflection in x-axis. When we have a negative sign inside, in this case, it's minus x inside. That means horizontal reflection. That means the line of reflection is going to be the y-axis. However, it's not going to be visible in this cos graph because if you think about it, this is what the cross graph looks like. It's symmetrical about the y-axis. Y-axis is kind of the line of symmetry. Even if you were to reflect it, we end up with the same graph, right? Because the reflection is the same, right? Even if you were to reflect this graph, the left side comes to the right, the right goes to the left. The graph is going to look exactly the same. Okay, but we could try it for another graph, for instance. We can't actually show this clearly for any of the trigonometric graphs. If you were to do it for sine, you could think of it like that yes, it is a reflection in y-axis, but the same thing is also looking like a reflection in the x-axis. But since it's minus x, what's actually happening is it's reflecting in y-axis in this case. But it's more clear if you were to use a different function. For example, if we had, for instance, a quadratic function, we will look at this later. Quadratic function which looks like this. This is the quadratic function. So basically, if you replace x with something else, so if I were to replace, for instance, x with minus x, you can see what happens. X with minus x, it will become minus x whole squared plus 2 times minus x. So when we replace x with minus x, you can see the two graphs are reflections of each other, right? The red graph and the green graph, they're reflection of each other. So if you focus on this part, for instance, this red part is reflection of this green. This green part is a reflection of this red part, and similarly, this green part is reflection of this red part in the y-axis. So the line of reflection is the y-axis here. Okay, so if we replace x with minus x, that's what happens. The graph is reflected in the y-axis. Now, let me go back there and summarize all of this that we've learned. So we talked about vertical transformations already before. Let me just copy all of this. And change this slightly for horizontal transformations. Just give me a minute. Okay. So let's see what happens with horizontal transformations. I'm sorry, I'm a lazy person, so I don't like to write a lot. So I just copied all of that. Horizontal transformations. All right. So what about horizontal transformations? In horizontal transformations, some change happens inside the function. And that in the earlier case, we had outside the function. Now something happens inside the function. Let's say we use cos here now. It would look like this. Cos of, you could have minus multiplied inside, or you could have a number multiplied inside, or you could have something added or subtracted inside. This is what the horizontal transformation would look like. Okay. Now let's talk about the first one. If it's multiplication with a negative sign, that means it's a reflection. And it's a reflection, it's a horizontal reflection. The movement of the graph is horizontal. Line of reflection is going to be the y-axis. Okay, so if you replace x with minus x, it's a reflection in y-axis. Okay, what about a? When we multiply x by some number, in transformation language, we call it a stretch. And again, I'm just going to write it down here for now. We will learn about stretch later in functions, but it's a stretch with scale factor 1 over a. Okay, but we'll come to that later. For now, this is what you need to understand. The period of the graph is going to be equal to the original period of the graph divided by a. For instance, if we had, for instance, this function, if we had y equals cos of 3x, what would the period of this graph be? Original period of the cos function is 360 degrees. Since we have 3 here, the new period is going to become 360 over 3, and that's 120 degrees. So now the graph will complete one full cycle in 120 degrees. Okay, if we had tan instead, we had tan of 3x, for instance, what about that? The original period of tan is 180 degrees. That would become 180 degrees over 3. If we had tan here instead, 180 over 3, and that gives us 60 degrees. So whatever was the original period of that graph, for cos and sine, it's 360 or 2 pi radians. For tan, it's 180 degrees or pi radians. Whatever the original period was, that gets divided by this number a. Okay? And then finally, we have translation, where we add or subtract something like this, plus minus b. Now, in this case, when in this function, you have plus b, that means the graph moves b units to the left. When you have minus b, the graph moves b units to the right. That's what translation looks like in this case. How is the vector going to look like? Now, the movement is horizontal. Y component is 0. What about the x component? If it's plus b, the vector is going to be minus b. If it's minus b in the function, the vector is going to be plus b. So we can write it as minus plus b, which means if we had a plus sign here, we would have a minus here. If we had a minus sign here, we would have a plus here. Okay, that's what the translation looks like. So let's take an example. Let's say we had something like this: y equals tan of x minus 180, or that will be actually a complete cycle. Let's do x minus 90. This is a translation of this vector 90, 0, which means 90 units right, 90 degrees to the right. That's what this transformation is. Any problem with this? Any questions on all of these different transformations? Horizontal transformations?
No, sir.
No? So now you need to remember all of these transformations, okay? Vertical transformations and horizontal transformations. In horizontal transformations now, only x coordinates changed and the operations that are applying are inside the function. So instead of x, you have something else. X gets multiplied with some number, or some number gets added or subtracted to x rather than the whole thing. Earlier in vertical transformations, something was happening outside this whole thing, outside sine of x. Operations were applying outside sine of x. Now they're applying inside the function. Instead of x, you have something else. Okay, so that's horizontal transformations. Now we can have a look at some questions from the worksheet on graphs. That completes our topic. We have covered all the concepts that we have in this topic. Now, if you have any questions, we will be discussing those questions today and most likely in the next class as well, because I think you are going to have questions. Yeah, so you can let me know what questions you have right now as well from the worksheet. Let's have a look at one or two right now, and then we can do more in the next class if you have questions. So I'm only going to be doing questions if you have problems. So make sure that you attempt the questions and let me know what problems you have. So yeah, did I ask you to attempt graph questions yesterday? Yes, right? Okay, so I hope you had a chance to attempt them, attempt at least a couple, two or three maybe. If not, make sure that you do that before Thursday, because Thursday is going to be the last session that we spend on this. If we do that, so I'm only going to be spending that session on trigonometry if you have questions. Otherwise, there's no point on me doing questions and you just looking at them, looking at me solving them. It's not helpful. So you have to make sure that you attempt the questions yourself, and then let me know what problems you have. We discuss those problems in class then. Okay, so let's have a look at this question that we're saying. Hazim, question number 27. Let's try this. And if you don't have any other questions right now, we can end the class for today. And then before the next class, please make sure that you have practiced from the worksheet and also have a look at some recent questions as well. And if there are any problems, let me know about them so we can discuss them. Question number 27. That's not graphs. Do you have any graph questions first? We could do this in the next class then. Does anyone have any graph questions? Any graph questions that you attempted and had problems in? Okay, how many of you are done with at least two graph questions from the worksheet? Can I have raise of hands? At least two graph questions from the worksheet. Rizal, you did not have any issues? No problem until now?
No, sir.
Okay, all right. So I'll give you time for until the next class to attempt those questions. Then let's have a look at this question for now. Then question number 27, and then we end this class. Make sure that you attempt those questions and also some more questions from recent papers, so that we can wrap this topic up in the next one. After this, we're starting coordinate geometry. We'll spend a couple of sessions on that just to cover some basics, or maybe 3 sessions. Apart from equation of circle, we will do the rest of the concepts and then move on to differentiation and integration. We will do equation of circle towards the end. The next topic is going to be coordinate geometry and then differentiation and then integration. Okay, that's going to be the order for the next few topics. Let's have a look at this one. Part 1. Okay, we need to prove this identity. 1 over sine theta minus 1 over tan theta. That's identical. The whole squared, that's identical to 1 minus cos theta over 1 plus cos theta. Haven't we done this before? This was one of the first few questions that we did on proving identities. Yeah, we have done this before. This was on Monday, 12th February. Hazem, was that the class that you missed? Monday, 12th February?
I don't think I missed the class, sir. I must have just forgotten.
Okay. Yeah, so we have actually done this question. You can find this in the notes as well and also in the recordings. Okay. So in this question, we talked about this, that it's better to convert tan to sine over theta in the beginning. And that makes things easier. Okay. Yeah, so have a look at the notes. You'll figure this out. Any other problems from the worksheet?
No, sir.
No. Okay, so what I'm going to do is I'm just going to have a look at one question myself. Okay, let's try this one, for instance. Question number 28 from the worksheet. Okay, it says sketch on a single diagram the graphs of y equals cos 2 theta and y equals 1 over 2 for theta between 0 and 2 pi. Now we have to draw these two graphs. How do you draw these two graphs? What you can do is you can use that table function on your calculator. Remember that. Now ClassWiz is going to be quite helpful here because you can make two tables at the same time, right? You can try that, make two tables at the same time and see what that gives you. So what you would do is you would say f of x equals, in fact, you don't need to do that, I'm sorry. This is just y equals 1 over 2. It's just a straight line. It's just a horizontal line. So you don't have to do anything for this. It's just a straight, it's a horizontal line. You just do it for cos 2 theta. Okay, so put this on your calculator. Instead of theta, put x, because it's f of x. So you'll have to put x here, and then use start, put 0 and 2 pi. Make sure your calculator is in radian mode. And then for step, you write pi over 4 so that you have enough values in that interval. Okay, let me make this graph. It's going to look like this. Okay, my other device has gotten disconnected for some reason. I'm not sure. I can't figure this out right now. So if you have a question or if you want to say something, respond to my questions, please make sure that you do that verbally, okay? Because I will not be able to look at the chat for the next few minutes now. Okay, so yeah, we have this x and y axis like this. This is the y-axis, this is the x-axis. We want to draw the graph from 0 to 2 pi, 0 to 2 pi. Let's break it down in the middle. This is pi, then this is going to be pi over 4, sorry, pi over 2. And then this is 3 pi over 2. Even though it's a sketch, please make sure the intervals are approximately equal. They should be spaced equally. Better, it's a good practice to use a scale for that measurement, so that you are not taking intervals that are very different from each other, because then your graph would not look good. Okay, so you have these intervals. We can break it down even further. This is pi over 4, then you have 3 pi over 4, then you just have values like this. Okay, now just do this on your calculator and see what values you get from your calculator. You'll see that the maximum point on the y-axis is going to be 1, and the minimum point on the y-axis is going to be -1. Now, when you do this on your calculator, keeping your calculator in radian mode, you will run into a problem, and that would be the table that they give you. The values of x in that table, they are going to be in decimal, so they would not be exact like this, right? However, since you know what interval you've taken, pi over 4, that means this is the interval that you've taken, right? This much. So you can just look at y values and just plot them like this at this interval. For example, the first value that you get is going to be 0. No, sorry, 1. If you input theta equal to 0, the value is going to be 1. And then, what about this? Pi over 4. Sorry, pi over 4. This should give you
0.7853.
I don't think so. Are you sure? I think it should be 0 instead. Remember, it's 2 theta. So make sure that you're writing the function correctly there. It should be 0, right? At pi over 4, it should be getting 0. And then at pi over 2, you would have -1. At 3 pi over 4, you'd have 0 again, and then 1 again, and then 0, and then -1, then 0, and 1. This is how the points are going to look like. Is that correct? Now, since you would remember the shape of the cos graph, remember how the graph looks like, you can just draw that shape here. It's going to be like this, and then this, and this. And then again, it goes like this, and you have 2 cycles completing in this interval. The reason for that is you've got 2 theta here. So period that was supposed to be 360 earlier, now it's 180. Or the period that was supposed to be 2 pi earlier, now it's pi. So you have 2 cycles completing. This is how the graph of cos 2 theta looks like. Okay. Then y equals 1 over 2. That's just supposed to be a horizontal line at 1 over 2. This point is 1 over 2. That's a horizontal line at 1 over 2. You draw that line for the same interval from 0 to 2 pi. This is y equals 1 over 2. And you make sure that you label these points as well. Labeling is important. Okay, so you have to label these graphs properly. And that's what you have to do in the first part. Okay, now the second part asks you to write down the number of roots of this equation 2 cos 2 theta minus 1 equal to 0 in the interval 0 to 2 pi. Now, how is this equation related to what you have done in the first part, the graphs that you've drawn? Remember graphs of functions, O levels? How did you use to solve equations like these using graphs? The graph that you've drawn, the major graph, the curve that you've drawn is basically y equals cos 2 theta. What you do in such problems is you basically write this equation in a form such that on one side of this equation, you get this thing. On one side of the equation, you get cos of 2 theta somehow. All right. How can we do that? We can make cos 2 theta the subject here. Take 1 to the right side and then take 2 to the right side as well. It becomes cos 2 theta equals 1 over 2. And if you think about it, these are exactly the two graphs that you've drawn in the first part. You have drawn y equals cos 2 theta. And you have drawn y equals 1 over 2. These are the two graphs that you have sketched in the first part. Right? Now, since you're looking for the number of roots of this equation, which is actually the same equation as this, where we are equating the two functions, you can just look at the points of intersection of these two graphs on the diagram. So you have 1, 2, 3, and 4 points of intersection. So what's the number of roots then? The number of roots is 4. That's what you have to write here. Is that okay? Any questions on this?
No, sir.
No?
Sir,
Yes.
sir, when I plot the graph, I get like at pi over 2, I get different value. I get like 0.7853.
Is your calculator in 0.7 pi over 2? Okay. Maybe you're just putting the function wrong. The function is cos of 2x.
No,
Are you
sir, I'm
sure
putting,
this?
yes, I put it cos of 2x.
Then start at 0 and end is
Yes,
2
sir.
pi and step is pi over 4.
Yes, sir.
Is your calculator in radian mode?
Yes, sir. I did it the second time and I put it in radian mode.
Okay, let me try this myself as well. Angle unit radian. Table f of x equals cos of 2x. Start 0 and 2 pi. Step pi divided by 4. You are looking at the values of x. Look at the values of f of x. F of x is y, right? Look at y values. The first value is 1. The next value is 0. Then you have -1. Then you have 0 and then 1. You're looking at x values. So the x values are basically 0 and then pi over 4. As I said, calculator is just converting these values in decimals. So the values that you're looking at are values of x, basically. So that's 0.7853, the first value that you're talking about. That's the value of x. The next value, 1.57, that's pi over 2. That's the value of x. You already know the values of x, right? This is 0, pi over 4, pi over 2. They've just
Yes, sir.
mentioned those values in decimals, right? Look at f of x, the second column. Okay? The last column, basically. Is that okay? All right. Let's get back to this question. So number of roots turned out to be 4. Okay, now let's look at the last part now. The last part says, deduce the number of roots of the equation 2 cos 2 theta minus 1 equals 0 in the interval 10 pi to 20 pi. It's that same equation. But the interval is different now. The interval is from 10 pi to 20 pi. What is the number of roots in this interval? Any idea? What's the number of roots in this interval? See, both of these graphs are basically repeating. So cos graph will keep going on like this, right? And horizontal line is of course going to stay horizontal, right?
Sir, 20.
Yeah. So the horizontal line is going to stay horizontal, right? Now, if in an interval of 2 pi units, we have 4 solutions, how many solutions would you have in the interval from 10 pi to 20 pi? That's an interval of 10 pi units. Just use ratio for that, right? So that's correct. From 0 to 2 pi, the interval is 2 pi. The number of solutions that you're getting is 4. From 10 pi to 20 pi, the interval is 10 pi. So if 2 pi is giving you 4 solutions, an interval of 10 pi should giving you 5 times that solution. That is 20. That's the result. Is that okay? So you can just write 20 there. There's no need to show any working. If you can just figure that out in your head, just write 20, and that's what is going to get that 1 mark. Is that all right?
Yes, sir.
Yes, sir.
Okay, now make sure that you attempt the rest of the questions and more from recent papers as well. And if you have problems, we will discuss them on Thursday then. Okay, I'll see you again on Thursday. Allah Hafiz.
I love it, sir.